Good day, everyone. You are welcome back to my YouTube channel. I am Engineer Biodun Oderinde. Today, we'll be talking about the part two of the test we carry out on Transformer. So please, we've discussed it part one. In part one, we talk about different type of tests we carry out and the reason why we carry out tests on Transformer. And this is part two. Please, if you enjoy our part one, this is our part two. Kindly like, share, follow us, and subscribe to our channel. Thank you so much. So today we'll be discussing about those tests in detail. Now we'll talk about winding resistance test. Winding resistance test is a particular test we carry out on transformer. So now we'll be telling us how we carry out the test and the analysis of each test. Now, winding resistance test, as I've said in the part one of this course. So it's also referred to as winding continuity test. Now, if there is anything that is missing here, please you can join us from the part one so that you get it in detail. We've discussed some things, the reason why we carry out tests and on transformer in part one. Now coming back to winding resistance test. Now, as I've said, how do we carry out winding resistance test and what is the analysis of winding resistance test? Now to carry out winding resistance test, we make use of multimeter. This is a typical multimeter. We make use of multimeter and we turn it on and we turn it to the knob to the resistance side. This multimeter, that's why we call it multimeter. You can use it to measure current, voltage or resistance. Now we want to measure the resistance of the coil now, so we turn it on, we turn the knob to what? To resistance section, and we use the probe to check the resistance. So we now check the resistance between the red and yellow, between yellow and blue, and between red and blue. As you can see my screen, AB, BC and AC. A is same thing as red, B is same thing as yellow, C is same thing as blue. So AB, that's yellow, that's red, yellow, BC, that's yellow, blue, and AC, that's red, blue. Now the resistance, that's what we do. We use the knob, we put it on the resistance side. We now check the resistance between red and blue, red and yellow. We check it, that's AB. We check it between yellow and blue, that's BC, and we check it between red and blue, that's AC. Now that's how we carry out resistance test on transformer. Now the analysis now. As we know that the transformer is three phase and each phase has their own coil separately. Inside, internally, this coil is being connected together. The red is being connected together with blue, with yellow, the blue is being connected with yellow, and these three coil are joined together internally. So there must be continuity between red and yellow, and between yellow and blue, and between red and blue. So there must be continuity. So as you can see this one, so and which means their value must be there, it must be continuous. So it must be continuous. That's one. Secondly, the value must be the same. The resistance value of AB must equal to BC must equal to AC. Why? Because these coils are made up of the same standard wire gauge. The coil inside the transformer, all of the three poles are made up of the same standard wire gauge. They must be of the same standard wire gauge. So now if they are of the same standard wire gauge, the resistance must be equal. That's first inference of what? Winding resistance. So two, they must have the same resistance. And also there must be continuity both at the primary side and at the secondary side. As you can see, a small ab, this when you see small letter a b c, that's what, that's your secondary side. And when you see capital letter a b c, that's your primary side. And you can see ab is equal to bc is equal to, that's equal to 52.1 ohms. For the primary, they must be equal and they must be continuous. So, and like this one for the small, for secondary side, we have AB, BC, and small CA for the, is equal to 0.1 for the secondary side. And also AN, BN, CN is equal to 0.1 for the second. They must be equal like this. If that transformer, before that transformer could pass what winding resistance test. As you can see this one, the remark is that it's okay. That's that about winding resistance test. The next step we'll discuss now is winding insulation test. So what do we understand by winding insulation? So the equipment we use to measure the winding insulation of a transformer is, we call it mega. That's, we call it insulation tester. The mega is just the brand name, it's just the vendor name. Those that produces, they are called mega. There are different type of the company. Different company produce insulation tester. It could be mega, it could be flux, um like that. So but the name is what? Insulation tester. But this particular one, the manufacturer is mega. So and it has different range. There is one of 1 kV, there's one of 2.5 kV, there's one of 2 kV, 5 kV, and like that. So now like this one now, we make use of 5 kV insulation tester. Now this is example of typical insulation tester. As you can see, this is a typical insulation tester. So we use it to measure what? To measure insulation resistance of a transformer. So how do we do that? Now as you can see my screen, there must be we all know what insulation is. Insulation is just a prevention, something that prevent the flow of current. It doesn't allow the electricity to pass through. When they say something is an insulator and conductor, a conductor allow electricity to pass through, while insulation prevent electricity from pass, it doesn't allow electricity to pass through. Now if the transformer have a good insulation, which mean there won't be leakages between the secondary winding and the primary winding. um they have both the primary winding and secondary winding, they are inside what? Inside the same main tank, and they are separated by insulation. There must not be leakages between primary winding and the secondary winding. There must not be leakages. So we need transformer that have good insulation, so that in the process of operation there will not be current that will be leaking from primary to secondary, because if the current is leaking, it could cause what we call short circuit, and at the long run it can affect the transformer. So there must not be leakages between what? Primary and secondary. That's why the transformer should have a good insulation. So as you can see, we have, there must be insulation between the primary side, that's HV side, and what? And the ground. There must be insulation between the secondary side, that's LV side, low voltage side, and the ground. HV, that's high voltage side. G is the ground. The ground we are talking about here is what? Is the body of the transformer. As you know, the body and the body of transformer must be grounded. So far the body of transformer is being grounded. So we refer to the body of transformer as ground because it's being connected to the earth. So now there must not be current leakages between the primary winding and the body of transformer, which is ground, because if it is, there will be current will be, so this is to prevent a kind of electrocution to the personnel and damage of the equipment of transformer to the equipment. There must be leakages. No current must be leaking from the primary winding to the body of transformer. So that's HV to ground, high voltage to ground, and LV, that's low voltage to ground. And also HV to LV. There must not be leakages of current between primary side and what? And secondary side. There must be enough insulation. So as you can see, this is how we measure it. So we have two probe. So if you want to measure insulation of the primary winding, the HV to ground, what we do is that we use this probe now, as you can see, we clip it to the primary winding, and we clip this other one to the secondary winding. That's how we do it, and we start the testing from this one, from our isolation tester. So if the transformer has good insulation, it must be of bigger ohms. You can see this one is 30 gig, 30 gigaohm. There must be enough insulation between the primary winding and the ground. um The higher the insulation value, the better the insulation of the transformer. As you can see, this one has 30 gigaohm, so which is better. Also, we have LV to the ground, the same thing. One of the probe, the red probe, will be clipped to the primary to the secondary winding, while the black probe will be clipped to what, to the body of the transformer, either the both there, anything on the body of the transformer, and you start the test. So it must be of higher gigaohms. So, and also between the primary winding and the secondary winding, in this case, the red probe will be clipped with the primary winding, and the black probe will be clipped with what, with the secondary winding, or vice versa. So we now start the measurement, testing. So that's how we do the testing on the isolation test on the transformer, and that's the reason why we do it, because there must be a proper insulation between them in order to prevent the current leakages. That's that on the isolation testing. The next test we'll talk about here now is about ratio test. Now, I said yesterday in my first class that we have single phase ratio test and three phase ratio test. In this class, we'll talk about only about single phase ratio test, and so that it will be clearer. So the next class we'll talk about the three phase, how to test three phase. But in this class now, we'll be talking about the single phase ratio test. How do you carry out single phase ratio test? um As you can see my screen, this was carried out by connecting AC input to the HV side of the transformer. um Red and yellow, that's A and B, yellow and blue, B and C, and blue and red and blue, that's A and C. Voltage was measured at HV side and LV side respectively. What this one is saying is that we make use of generator. Generator is single phase generator, a phase and a neutral. So will be connected. The phase and neutral will be connected to the primary side of the transformer. We first connect it to AB, as you can see here, AB, that is red and yellow. We connect it there. If you connect it here, we now measure the voltage on A and B at that primary side. We will measure the voltage on B and C, that is yellow and blue, on the primary side. We measure the voltage on A and C, that is red and blue, on the primary side. After that, we still go to the secondary side. We measure the voltage on A and blue, that is red and yellow, blue and yellow and blue, and red and blue, like that. And we still measure it on the neutral side. The red phase and neutral will measure the value of the voltage. The blue phase and the yellow phase and neutral will measure it, and the blue phase and neutral will measure it. We have this value as an example. So also, after that one, we now remove the probe. We put it again on yellow phase and blue phase. We still do the same thing. We measure AB, BC, AC, and like that. We remove it, we put the probe back on red and blue. We will measure the voltage again across the line, as you are seeing it. Now, that's how we carry out single phase ratio test on the transformer. Now, what is the interpretation? How can you analyze it? How are you going to know that this one pass the ratio test or no, or not? Now, the first thing is that you need to look at is that, as you see this one, we have our supply voltage, is because we connect the voltage on the supply on A and B, red and blue. So that's why when you measure it on red and blue, you see all your full voltage there. So this is the voltage coming from the transformer, because you can only see it here because you connect it to A and B. Now on B and C, you see 207, and on A and C you see 19. Why? Because this one, you don't connect anything to this one. The voltage you are seeing here is induced EMF, is induced voltage, and it's because this side B and C is closer to A and B. That's why you see 207 here, and A and C is somehow farther to A and B. That's why you see 19 here. But the essence of this thing is that the addition of this and this, A, B and C, and A and C must be equal to A and B. So that's the first step to know that this ratio test is okay. That's the first step. The addition of these two must be equal to this. And on this BC, remember you connect it to B and C, your supply to B and C, that is yellow and blue. That's why you have a full footage here, as you can see. That's why you go have a full footage on yellow and blue. And now, as you can see, so this 130 is just an induced EMF, and 87 here is an induced EMF. So this one, the addition of 130 and 87 must always equal or almost equal to 226. There will always be a variation. There's nothing like a perfect situation. So, but addition of this and this must be equal to this. If you look this and this and this and this, you see that the difference between this and this is not too much as compared to this one and this one. It's because this 226 in this case, is in between this and this. That's why you have the variation not too much. But the essence is that the addition of AC and AB must be equal or almost equal to BC. So the same thing, A and C, that is red and blue. As you can see, you connect to red and blue, you see it here. You see all the full footage here because we connected it with what? A and C. So that's why you could see the full footage. And also, the addition of AB and BC must equal to or almost equal to AC. As you can see, BC is closer to AC. That's why you have much footage here, and this one is smaller as compared to this. So, but the addition of this one, AB and BC, should equal or almost equal to AC, which is 2 That's on this side, on primary side. Now you come to secondary side too, you can see the same thing. The addition of A, B, C, and AC is almost or equal to what? AB, 2.9. Also, the addition of BC in this case and AC is almost equal or equal to what? AB. In this side of the secondary side, the addition of the two must equal to one, but it depend this one, the highest one can be in any place, unlike this one, the highest value will be at the point where we connect it. But at this secondary side is what? Is a line voltage at the secondary, while this side AN, BN, CN is a phase voltage at the secondary side. So for the lines voltage at the secondary side, the addition of the two must can be anywhere. As you can see this one, this addition of this one is here. The addition of this one and this one is here. But in this case, the addition of this one and this one is here. In this, the line voltage for the secondary side, the addition of the two can be anywhere. But when you come to phase voltage here, the addition of the two will be in the position where we have this one. If it is DY N11. As you can see in this AB now, the addition of this one is equal to 226. So in this one now, the addition of BN and CN is we have it what? In AN, which is equivalent to the arrangement is the same thing with what we have here. So here now, the addition of this one and this one, AN and CN is equal to BN. The addition of AN and BN is equal to what? Is equal to CN. So you can see it's diagonal. It's diagonal like this one. This one is DYN1. In our next lecture, we'll be talking about the vector group. When we get there, you will understand what I'm saying better in this case. But you should all know that this transformer is DYN1. That's why N11. That's why we have it like this. If it is DYN1, it will be in another, the arrangement will be in another dimension. But the main thing here is that the addition of the two must be equal to one, like we have it here and here. And if it is DYN1, if that transformer pass ratio test, it must be at this side, it must be diagonal. It must be in diagonal like this. You can see 1.4, 1.4, wow, it must be in diagonal. If the transformer like this one now, this one is okay, and you have the remark to be okay. That's the how we test the ratio test, and that's the analysis. That's the analysis. What this one is saying is that we want to know the ratio transformation. between the primary winding and the secondary winding. That's the interpretation of single phase ratio test, the ratio transformation. That is, if truly this transformer is 33,415 or 11, let's see the voltage rate of this transformer is 33,415. As you can see, the voltage rate is 33, is 300 kVA, 33,415. So if this transformer 300 kVA is truly 33,415, so we want to confirm that if you connect 33, are we going to have that 415 as said in the specification? That's essence of what? Of ratio test. So we now use a particular footage, we connect it. So we must have a value here. So the value here, we now use, this is the measured value. We now have a calculated value. The calculated value must be equal to the measured value if truly this ratio test is okay. There's a way we do a calculation for calculated value, and how we do it is that we will equate 33,000 to 415, because this particular one is 33,415. If it is 11,415, 11,415, so we equate 11,000 to 415. But in this case, it's 33,000 to 415. We say 33,000 equate to what? 415. And this is our applied voltage at this point. We now equate it, we now 226, we put X. So if you put X, do quad multiplication, we must get 2.9, the highest value here, or almost equal to 2.9. So if you have that one, that shows that the ratio is okay. The calculated value must equal or almost equal to what? To the measured value, which is we now consider the highest. And also, to get the this is the line voltage and this is the phase voltage. You should know that if you want to get phase voltage from the what? From the line voltage, you just divide the phase voltage by line voltage by what? By √3. That's how we get phase voltage. Thank you. So that's that about a single phase ratio test. Now let's talk about single phase short circuit test. Another name for short circuit test is also called capacity test. We use single phase short circuit to confirm the capacity of the transformer. If they say the transformer is 300 kVA, we need to confirm that is it 300 kVA, because the transformer could be a refurbished. They may just paste 300 kVA as the nameplate, but meanwhile maybe they've work on the on the transformer, they've changed the coil inside the transformer, it may not be 300 kVA like again. We have instances like this, that we have it on the nameplate of the transformer to be a particular capacity, but if you do the ratio the short circuit test, it may not be. So that's why it's very important, especially when we are doing pre-commissioning test. It's very important to do the short circuit test or capacity to really know the capacity of that transformer, because we need to know. Because if they told us that that transformer is 300 kVA, for example, we need to have it in our database. But if we put 300 kVA in our database and we subject it to the load of 300 kVA, meanwhile it's not 300 kVA. They've worked on the coil, they've changed the coil, and they've put what we have there is 200 kVA, and we believe, we will be thinking it's still that 300 kVA. We'll be subjecting the load of 300 kVA to it. At the long run, the transformer will get damaged. That's why it's important to really confirm the capacity. So that's the essence of short circuit test or capacity test. And how do we do it? We make use of the multimeter tool, and generator, as in the ratio test too. You can see, but in this case we do it at the secondary side. The secondary side ABC of the transformer will be short circuit. In some cases you can short circuit this red, yellow, blue, or you can short circuit red, yellow, blue, neutral. You can short circuit it with neutral, but the best is to short circuit it with neutral for critical analysis. But if you short it the red, yellow and blue together, you still get your result. But when you want to do critical analysis of that test, you have to short it with what? With the neutral. So if you short it, in this case now they didn't short it with neutral, they short A, B and C, red, yellow, blue. They will short it. They will use a copper wire to connect. That's what I mean by short. They will connect the red phase and blue, they will connect together. So when they connect together, they will now AC input will be applied to the what? To the primary side. The primary side they will now collect AB, as you can see, they collect AB. So this is our fish or circuit, our footage we supply on from our generator. AB, we connect it, we put supply, the live and neutral from the generator, we put it on AB. We now measure. In this case, what we are measuring is the current. We use our clamp meter. This is the clamp meter, this is the multimeter. There's some multimeter that is ammeter, that has ammeter. There are some multimeter that doesn't have ammeter. This is what we call ammeter. We use ammeter to measure current. um So you put it in current, AC current, and you clamp it. We are going to clamp the what? The cable. So with this we are going to get the what? Our current. So we now clamp red face, as you see, red face 0.6, clamp blue face and C. If you clamp the C, you get 0 because there is no cable on it. You just connect the cable on A and B and you no have value here, you have 0. But at the secondary side, you have the value A, B and C. And also here, the summation of A, B and C must equal to A, as in case of ratio test. The summation of these two must equal to 2 because all the current will be flowing on what? On the this phase, on A. But the summation, the current that is flowing here is due to induced current. These are the induced current, but the summation of the two induced current must equal to what? To the main current that is flowing. So that's that. And like this one now, we change the knob again. We put it on what? On BC, that is yellow and blue. So you can see that first is yellow and blue. BC we put on this A doesn't have value to be 0. When you measure it, you have value, and all these value will be the same or almost the same. You can see. So you can see here, we have it here. So at the summation of this and this must be equal to this. So like this also. So now if you connect it to neutral, you short neutral with it. Ordinarily, that's why I said for critical analysis, you must short it with neutral. Because if you connect it, if you short it with the neutral, if the transformer is okay, is perfect, you will not have current on the neutral. But if the transformer has issue, you easily see it on the current will be flowing on the neutral. Though if you short it, if you have lower current, you may ignore it because there is no perfect situation. But when it's getting higher, more than 10%, you know that there's problem with that transformer. So apart from using it to calculate the what? The capacity, you can use it to analyze whether the transformer is okay or not. But if you want to analyze it, is it like this? This and this must equal to this. As you can see, this and this must equal to this, and this must equal to this. And if you short it with the neutral, there must no current flowing in the neutral. But as we know that there is no perfect situation, in some cases you might be having little current flowing, but the current should not be much. Ensures that if is higher, is more than 10% of the primary current, you know that there's a problem with that transformer. So that's that. And now, how do we now calculate the capacity? So this is the short circuit. We use this short circuit measure reading to calculate the capacity. You can see. So this is we have a particular formula that we use to calculate the capacity of transformer. This is capacity calculation. We have this is VA, this is power. VA is called to root 3. VP, that's primary current, primary voltage. VA secondary voltage. Z is impedance, and I short circuit V short, as you can see. Root 3 is 1.732. VP, that's primary voltage. If it's 33,415, your VP will be 33 kV. If it's 11,415, your VP will be 11 kV. And your VS is the same thing, either because it's either 33,415 or 11,415. It will be 415 volt or 0.415 kilovolt. You can see 33 kilovolt or 3,000 volt. But when you are doing calculation, you have to take it to SI unit, and this is impedance. Impedance of every transformer has impedance. Impedance is like a resistance in to what? To flow of current. Every transformer will have impedance, and we have impedance in the nameplate. There must be impedance in, so we get this impedance from our nameplate. and this is high short circuit. How do we get high short circuit? Is from this